Hello and welcome to Biology Interest. Today we're not quite looking at something biology related, but a bit more chemistry related. We're going to be looking at the electrophilic and nucleophilic reactions in chemistry A level. So there's four main ones we need to look at. That's electrophilic addition, nucleophilic addition, electrophilic substitution, nucleophilic substitution. That's what we're going to be looking at today. So let's start with electrophilic addition up here. Okay, electrophilic addition. And so this is essentially when you add something across a double bond. So it's to do with double bonds essentially in something like an alkene. So let's write that out. So let's have ethene and hydrogen bromide. So something like, in fact, let's make it butene. That's probably better. But let's draw it like this. So, because it makes it clearer to see the double bond. So, we've got the double bond here. And then we're going to have, the best way to draw it is probably to have our hydrogen bromide here, like this. And because we're going to be attacking the double bond with the more positive hydrogen, essentially. And so basically what happens here is that let's write it out, draw it out, that the bond is broken here. And so we draw that with a curly arrow to show that the electron returns to the Br because it becomes more negative, and this one has a delta positive. And because of that, the electron travels from here to attach to the hydrogen there. And so basically when that happens, we go to the intermediate step. So if we go to the intermediate step, we see that we've got our bond broken, but we now have a hydrogen attached here, and we have a space open for bromine, essentially. So we have a positive charge here, and because bromine now got bonded, given 2 electrons when the bond broke between hydrogen and bromine, we now have a negative bromine ion with 2 free electrons. And so that electron pair is essentially just going to go and bind with the positive charge on the carbon, because the carbon only has 3 bonds. And that is essentially just going to form this. So if we just run out of space here, but if we just draw this here, we now have a bromine and a hydrogen added across a double bond. And a similar thing will happen if you have Br2, but you'll get 2 bromines here instead. So that's quite good. So that's electrophilic addition, quite an easy one. We're now going to look at electrophilic substitution down here. So let's look at it down here. Let's just move the board up a little bit. Electrophilic So electrophilic substitution. Now this is generally to do with benzene rings or phenol rings, essentially. So as long as you remember it's to do with that, it's fairly easy to remember which one you're doing when you get to it. So we're going to draw our benzene ring. And we're going to do the electrophilic substitution with an NO2 plus electrophile. But the ones you need to know for chemistry, OCR at least, A level, are NO2 plus, Br plus, Cl plus nucleophiles. Although to get a positive charge on them, you're probably going to need some kind of halogen carrier with it. Because normally the electron density is not high enough to in the benzene ring is not high enough to polarize Br2 to make it become an electrophile. But having an electron carrier do that for you is what you need, really. So the best way to draw this mechanism is to have the NO2 plus here, and then you have to draw the arrow coming from the benzene ring of electrons, of delocalized electrons, to the NO2. Then if we go to our next step, we can see that we draw it like this. And let's say we're attaching the NO2 to the first carbon. We have to draw the ring like that to show that it's been broken where the thing is joining. Then we have to draw a hydrogen being attached and an NO2 attached. Because normally there's one hydrogen being attached, but what you're essentially doing is you're replacing the hydrogen with the NO2. And so you show this electron being taken back into the delocalized ring. So if you look at it, you've taken out an electron from the delocalized ring to attach the NO2 to the benzene. But by doing that, you've broken the delocalized ring, and that's more positive because there's less electrons in there. So you need to return the electron from the extra hydrogen to the ring. And then essentially that just breaks off. And you now have a closed ring with an NO2 attached and a free hydrogen floating around that can go and bind with something. And so that's electrophilic substitution. It's pretty much the same for every single other electrophilic substitution, although it depends where it's being placed depending on the directing groups involved, if it's phenol, etc. like that. So you'll need to brush up on that. I know I probably will. So next, let's look at the nucleophilic reactions, which are slightly different because they're to do with the nucleus, the atoms inside most of the time. So if we look at nucleophilic addition, if we look at that, we can do something like this. So if we have a CH3, a carbon and a CH3 with a double bonded oxygen, so a ketone, we can then attach something like a NaBH4 or a NaCN as the nucleophile. So in this case, with this one, what you have is you have the electrons actually going from this bond here being pushed away to the oxygen, and the oxygen becoming more negative, causing the carbon to become more positive, because you have a negative hydrogen atom attacking the carbon and making it more positive, essentially. And so when that happens, you essentially get a one bonded oxygen that now is negatively charged because it's received an extra electron from the bond, and a hydrogen has now been attached down here. So if we look at that, and then basically what happens is you have to have water or another free hydrogen basically somewhere else, and that can attach here to the oxygen. So the bonds will go to a free hydrogen, something like attached to water or something like that, that will then bond with this. And if we show this down here for the final step, we see that we now have this with a OH with a CH3 and a hydrogen. So that's how the nucleophilic addition mechanism works. It's similarly, if you were using NaCN, you would have something like this produced. So so instead of the hydrogen being attached, you would have the CN being attached, I believe. So the final one is going to be nucleophilic substitution. Now this is probably the least used one, but it's similar to the nucleophilic addition in the way that it's like a carbon atom that's being attacked by something, by a nucleophile. So if we just drew out this, this molecule, so you would see that it's not really open to much attack, but if it's being attacked by something like this, so it's basically just a triple bonded carbon, so it's negative because it's got a free pair of electrons, and so that's pretty much going to just attack the carbon and make it positive by pushing electrons away to the Cl, which gains a negative charge. And basically when it does that, the Cl is essentially going to break off almost because it's got less of a negative charge than the carbon and it's being pushed away. And then you basically just get this, where you get the carbon being attached, like that. So CN's a pretty powerful nucleophile most of the time. So this is quite similar to that one. You just have a Cl being given off because it's being pushed away. But other than that, so while remembering your mechanisms is a bit of a pain, once you understand them, shouldn't be too bad when you know when to use them at the right time. Stay tuned, please like and subscribe. Thank you.